this might actually be something useful for the Neuromatch listeners out there.
Maybe we should briefly talk about the concept of normative models, no? Because I think all four of us are deeply committed to that way of thinking. Why are we so excited about normative models?
Math is so cool because you can take reality and kind of transfer it to this space where you can do operations and get something new and then come back, and that will still correspond to reality.
I think if you want to be really original, you're going to have to give up some coolness, because there are many people who are entering the field kind of swept by this wave of enthusiasm for certain ideas like deep learning. And what that means is that many people are basically doing more or less the same thing.
If you're still working on the same thing you told your hiring committee you would work on 10 years later, then something has gone wrong. And probably most people find their questions because their data don't make sense without different questions.
This is Brain Inspired.
Hi, everyone. I'm Paul. This is the last discussion panel of the first round of Neuromatch Academy, where we are ostensibly talking about stochastic processes, Bayesian inference and models, decision-making, optimal control, reinforcement learning, causality. Those were the topics for the past week in Neuromatch. With me today are Yael Niv from Princeton University, Konrad Kording from the University of Pennsylvania, Tim Behrens at University of Oxford, and Sam Gershman from Harvard University. And three of those people, Konrad, Tim, and Sam, you've heard multiple times on the podcast before, but Yael is a new person on the podcast, so it was really nice to have her. So we do talk high level about some of the topics related to this past week, especially normativity and why these models are good models to use to understand brain function. And then we go on to talk about a host of topics related to just doing science and thinking about these sorts of things, where questions come from and how to get a good question. I make the fun mistake of calling mathematical and computational approaches to the brain sterile, by which I meant no harm, but it sets off quite a discussion that then winds its way among many other topics. For the record, I call this approach sterile in terms of its purchase on matters of connecting brain function to subjective experience, qua philosophy of mind. And that set off a fun flagellation of me, which was fun. I link to all the guests and to Neuromatch Academy in the show notes, braininspired.co/podcast/NMA-3. Okay, enough of me. Better things await you. And here are those better and fruitful, I hope, things. So what I'd love for you to do is just introduce yourself, what you do generally, very high level, and then what I would like you to say, just as an example, as a personal example, what do you think you're best known for, and what are you most proud of in your work? So Konrad, perhaps we should just start with you, the Neuromatch central person here.
Well, thanks for having me. I'm Konrad Kording. I'm one of the co-founders of the Neuromatch movement. I deeply believe in accessible teaching and communication in the field. I'm probably best known for Bayesian models of how we might be thinking. And I think I'm most proud about thinking about the epistemology behind neuroscience.
Nice. Proud of the thinking. So that hasn't...
That's right, exactly. So I've been struggling for years with how I want to think about brains, and I oscillate between many different views. And I think I'm seriously most proud about giving like all these different ways of thinking a brain in a way like what I feel to be a fair shake, despite the fact that I'm deeply opinionated, obviously.
I imagine that's a trait of many among the panel here. Yael, who are you, and what do you do, and what are you best known for, and what are you most proud of?
Hi, I'm Yael Niv. I am at Princeton University. What am I best known for? I think I might be best known for reminding people who study reinforcement learning that we should think about how states enter into the picture. So how people and animals learn what are the states of a task or what's the structure of a task. What am I most proud of? Actually, you can ask Sam later what I'm best known for, because he was making some kind of face that made me think I'm saying the wrong thing here.
Well, I was just going to say that now I don't have to say what I'm best known for anymore.
That's right. I'm best known for what Sam discovered when he was in my lab.
No. I'm not trying to steal your thunder, Yael. I'm just saying that I'm best known for probably the work that I did with you.
Yes. Well, similarly here, I'm best known for the work that you did when you were in my lab. And actually, that goes well with what I'm most proud of. I was trying to think really quickly because I didn't think of this before. Maybe you asked us to do that, but I didn't. What am I most proud of? And I think that's the fact that I once got a graduate mentoring award.
Early on. That was an early on career thing. That tends to be a common answer is when, a reward that you got as a faculty member mentoring a graduate student. Is that what that is?
Yes, I got a graduate mentoring award as faculty. Not that early on, a couple of years ago.
Yeah, very good. Tim, let's swing it to you. Who the heck are you, Tim? What do you do? What are you proud of, and what are you known for?
So I'm Tim Behrens. I guess I'm probably best known, I don't really know, but I made some software that is popular for figuring out brain connections. And so I guess that's certainly what I'm most cited for. So let's assume I'm best known for that too. I'm most proud of, I don't know, maybe there's like diversity of stuff that I've dipped my nose in or something. I mean, like I sort of feel like I've tackled a few different problems, always with a couple of themes. So I tried to think of new ways of thinking about data. So trying to see what you can measure that we couldn't measure before. And I often try to, I think that something isn't solved until you can see it in more than one species and more than one technique and that kind of stuff. So that's mostly what I do.
Thinking about that diversity, I mean, all of you on this panel have expressed that diversity in interests and in your works, which kind of goes against maybe common, what you're supposed to do is dive really deeply into one topic or two topics, right? And that's the way you make your bones. But I mean, everyone's shaking their head. So
there's different models. I agree with you that you should go deep, but you don't have to stay with. Often, when you go really deep, you find that you're related to something else. I think, and in an interesting way. And so I think that being this ability to think, to see relationships across different things, I think is another powerful way that academics make their mark. There's the guy that entered the guy that invented MRI, who shamefully, well, I mean, he didn't. This is actually. This is wrong. He's got a Nobel Prize for his contribution to nuclear magnetic resonance, and I think it was Hahn, although I can't remember. But somebody else will remember better when I say that he also figured out the dynamics of motion of bacteria and things like that using the same kind of physical principles that he discovered for NMR. I think it was Hahn. I think I
wanted to say that you're also talking to a group of theoreticians here. Maybe this is a little bit more characteristic of theoreticians, that it's not only what Tim is saying that you take one method and find connections in different places, but sometimes what I find with myself and a few of my colleagues who are theoreticians is we're interested in a problem. We make, some headway in it, clearly not solve it in like the solve term, and then kind of lose interest in it. And it's like, okay, so what's the next problem I'm going to solve? I mean, some people, again, there are different ways to do this. Some people spend their whole career on one problem, and some people after 3-5 years are like, okay, done with that. Now let's go to the next thing.
I think what Tim is expressing is a somewhat different sentiment. I'm not saying that doesn't happen, but I resonate with what Tim was saying in the sense that what going deep really means in some cases is to attain a level of abstraction in your thinking about a problem that renders visible connections that you didn't see before, right? And so deep is not the same as just drilling down in the same topic forever.
Well, Sam, I was going to say, you may be best known for not being very deep yourself. So let's, but other people would have
What's that supposed to mean?
I don't know. I just wanted to give it a little spice. Sam, who are you? What do you do? What are you best known for and most proud of?
I'm a professor at Harvard, and I think we already covered what I'm best known for. I guess possibly my work with Yael.
And you should say what that was about. You should say something about latent causes.
Everybody knows he's best known for it, so everybody already knows.
Right.
It's also been. I mean, no discredit to Yael, but it's also been massively developed in your own life as faculty as well. Yeah. And so it's worth noting that is a major achievement that you're also well known for.
Yeah. Yes, it's the problem, I would say, broadly speaking, of structure learning. How do we discover the structure of the world around us? And that has many different manifestations in reinforcement learning and beyond. As far as what I'm most proud of, I really have to go with the people answer, which is I'm most proud of the students and postdocs that have gone through my lab, because that's really the gift that keeps on giving.
Okay, so I just had to look back because there's a lot of topics that were covered throughout the week. There's Bayesian topics, decision making, optimal control, reinforcement learning, and causality. So I guess our conversation should be centered around these topics loosely. We can't drill down into all of them. But maybe one way to start this off is to ask where you guys think which of these topics has the most fruit to offer in terms of connecting, because these are it's computational neuroscience. Computations are sterile mathematical objects. Which of these, I just threw sterile in there for fun, but which has the most fruit to offer in terms of connecting minds with brains, or what we think of as minds?
So I think I'd zoom out in a way. I think it's this week that has a lot to offer, which is in the first week, we learned a lot about the basics and techniques, whereas this week we learn about these concepts that we can relate to the way we think in a way much more than maybe what we did in the first week.
So I mean, I think both Bayes and RL, which are two things that are close to all of our hearts on this call, are both tools and models of the brain. And thinking of them in both of those ways is informative and exciting, because it means that you can imagine how your brain might be working in the same way as how you can be analyzing your data, which I think is, I mean, that's something that I always love. I love the fact that with Bayes, what you have to really specify if you're going to solve a problem is a generative model, and the rest of it you then choose between the sort of Bayesian toolkit that's available. But once you understand what the problem is, that is enough to specify the solution. And somehow that's what I think is there's something purely elegant about that, because really as a theoretician, your job is to understand the problem, not to solve the solution. And there's something beautiful about imagining the brain that way. Really, what it's trying to do is understand the problem, the world around it as the problem, build a forward model of that, and then it can learn that inversion somehow. So there's something beautiful thinking about that way. And you can actually express reinforcement learning in those same terms as well if you choose to.
Also, these two theories are both normative. So, Bayesian inference is a kind of statistically optimal way to integrate information, and reinforcement learning is a optimal way to learn predictions, to learn expectations. So in that sense, I think what Tim was saying is both of them we can use them as data analysis methods. For instance, when we get data and we want to, extract information from it, we can use these methods, especially Bayesian inference, as tools, that you could use in many areas. But then our brain does that too. because our brain is so optimal and awesome. Just the other day, my son asked me if our neurons compute all kinds of things and can do exponents, how come we don't know how to do exponents when we are babies? And so, yeah, our brain knows how to do Bayesian, really optimal, awesome stuff that we don't know how to do yet as researchers. Yeah.
What age do they start asking those kind of questions?
My son he's 9.5.
Is it Eitan? Wow. So
it's Oren.
2 years old. So it was Oren. Okay.
So maybe we should briefly talk about the concept of normative models, no? Because I think all four of us are deeply committed to that way of thinking. Why are we so excited about normative models?
I don't think that we should shackle ourselves to normative models. I tend to think of normative models more as a kind of starting point for thinking about the problem. Like I thought Tim put it very well. One way of approaching the complexity of the brain is to say that there are certain problems that the brain is trying to solve. We can stipulate some assumptions that we impute to the brain. And then once we've basically specified the problem, we can ask we try to characterize the solution and ask whether that is at all similar to what we can measure about brain and behavior. But that doesn't necessarily mean that we have that all of our models have to be purely normative. There are points in the modeling process where we have to kind of adapt them to the biological constraints, which might also be normative, but it's not always obvious what they are. Sometimes they're just kind of empirical constraints.
Yeah, I mean, like for me, the drive towards normative thinking drives from me kind of, I feel like I understand those aspects. It's the normative models are usually of the flavor where I say something, in the world, there's noise in the way you move your muscles. Or in the world, there's noise in the way we perceive things. And it feels like those are things that I can understand because they're not relating to the brain, which I'm very conflicted about what we know. There's something about the world. And then ideal behavior, optimal behavior, like derives from the understanding that we have about the world. And as scientists, we're very used to talking and thinking about the world. And so in that sense, for me, at least, the drive towards normative models comes from a sense of humility about what I feel I really understand about the brain.
You feel like you understand optimality assumptions? I mean, I'm not saying that you can certainly write down a mathematical equation, right, and say, I understand the equation, right? But you feel like you understand the biology well enough to say, all right, these are the optimality equations that the brain is actually solving.
Well, I don't think we know which optimality equations our brain is really solving, but we have an idea about that. Like we are talking in most cases about humans trying to do certain things. And if you play tennis or something, I know that you're trying to score points. I don't need to understand the whole properties of your brain to get at meaningful models. And if you come to my lab and we do an experiment with you, I will pay you based on the points that you make in that game. So in that sense, there exists a lot of, and even in areas where it's not so clear, let's say soccer, where you could say, well, there's this thing of how well I guard space. And sorry again, Tim, for the Euro Cup, but we reason about it. Like our language is full of things about what we are trying to achieve.
I think that there's a risk there of missing out on a lot of things that we're trying to achieve as humans, which are all the social things that we're trying to achieve. Even while you're playing tennis, you're trying to score points, but maybe you want to shame the other person. Maybe not. Maybe you want the audience to like you. Maybe you want, who knows what else. You might not be super aware of that. You might not report it, but it might be driving a lot of your actions. And I think one of the things that we, there's been a lot of advance in cognitive neuroscience, thinking of a person as a single unit that a brain in isolation, but actually in the real world, we're such social animals. So we've missed a lot. And that's maybe, where we should go next. And I think where Sam is going with his research is really bringing in the social component.
I mean, there are a lot of people who are thinking about sort of cognitive neuroscience. It's possible they're not thinking about it with the same naturalistic way you're thinking about, but there's it's just worth pointing out that there are.
Oh yeah. No, I didn't mean that nobody's researched about like us here in this conversation saying, we know what people are optimizing. That misses a lot, maybe with their motor actions. I want to, not spill the coffee from my cup, but that's just such a small part of our world of what we're optimizing.
Konrad knows what people are optimizing. I don't know if I know what people are optimizing.
So when it comes to social things, I think it's not true that we don't have good ways of starting to think about it. Like people spend a surprising amount of their days talking about social relation. Hey, I would like to convince them that I know what I'm doing. I'm worried they're judging me. Like a lot of human language is exactly about what we are optimizing in social relations. So I don't think that space is fundamentally different.
Maybe for the Neuromatch people, sorry to move us away off social neuroscience, but I think probably that's not our collective area of expertise. Maybe it is worth just specifying this difference between a normative model and what the alternatives are. And so, I mean, I suppose in some sense, there are models that we know do something as a model of the brain. And then we ask, well, here's the model that does something. Does it look like what the brain does it? And let's class all of those as normative. I know that there's going to be debate about that, but let's put convnets and all that kind of stuff in that class of models.
Kind of the what model? The answer to the question of what does the brain do, not, for instance, how does it do it?
Well, even with a convnet or with something like this Tolman Eichmann machine that I've built, you can say, okay, let's look at the it's solving a problem. I understand what problem it's solving, and I can look inside the representations, and they look similar to what the brain does. There's that kind of model, or there's a model of, or you can take that kind of thing without anything about the brain at all, and just look at the behavior, as Yael says, or what model. But then there are like other types of models that are models directly of the data, or there are models, or there are models of the brain that just try to predict how the neurons interact with each other without knowing
process model.
Yeah, exactly, the process, without considering what the problem is the neurons are trying to solve. I guess those are the sort of three classes of models, and
they could consider, they can consider what problem is being solved, but they're more focused on how is that problem solved rather than what is the problem that is being solved.
Yeah. Okay. Yeah. Yes.
I mean, if you have a circuit model of how a neuron can compute a prediction error, the problem is compute a prediction error, and you can say, here's how the circuit can do it. But it's not asking why should you compute a prediction error to start with.
That's what I thought, as I just would need to press go with you guys, and I didn't expect to talk again. So, but
I wanted to say one more thing. Gosh, now I can't remember exactly what it was linked to before. But Paul, you said that math is these. How did you describe it?
Sterile.
Sterile. You said that like we're computational people, and then math is sterile computational stuff.
I didn't call you sterile. I said the computational approach is kind of sterile.
Wanted to say that there's this awesome book called Dialogues on Mathematics by Alfred Rennie that has like 3 short dialogues on like why is math relevant? Like why do we care about math in the form of dialogues between like Achilles and the tortoise or something like that. And the main point there is that math is so cool because you can take reality and kind of transfer it to this space where you can do operations and get something new and then come back and that will still correspond to reality. So like it's hard to do operations on things in the world, but it's easy to do operations on things in math and maintain kind of truthness when you translate back. And I think in that sense, these normative models or the classes of models that we're talking about they're this abstraction that you can work with to understand things about the brain, even if every part of the process is not how the brain does that process. So the brain has to do a lot of, satisficing and taking, really hard computational problems. You just a lot of things we can't even solve optimally, even with like supercomputers with Bayesian inference, because they're just too big and the brain just does this all the time. So it must have some shortcuts to do this. But we can move in the mathematical space. We don't know how to move in the brain space. And then we get to something and we're like, okay, so the brain should in the end have, as a product of the computations, this and that. And you go back to the brain and you're like, oh, lo and behold, or at least you go back to behavior and you see, lo and behold, there are signatures of this mathematical quantity there, even if you don't know how the brain computed it.
Well, when I was talking about the sterility of the computational approaches, what I was trying to link it to was mind, because there is brain and there's the implementation of how it happens in the brain. But at that abstract level in mathematics, does that help us connect to what we think of as mind, subjective experience that many of us got into
Paul,
this
let me
racket.
stop you right there. In what sense is mind subjective experience?
Well,
right?
so it depends on how you define mind.
Is part of mind, right?
It all depends on how you define mind, but people commonly think, what I mean is subjective experience. That's what I mean, because that's the connection that is, that's the question. Is there a connection? Do the computational models help you think? And I know that subjective experience is not the goal of the computational neuroscience program at Neuromatch, so we don't need to go down that road, but that was more the upper level question. I think of mind as just the functioning of the brain. So,
but I think, Paul, I feel like it's very illuminating what you just said, because I actually think a lot of neuroscientists think in this way, which is that there's all the mechanistic stuff that happens with the neurons, and then there's mind, and mind is all the subjective stuff that we experience, our phenomenal experience. And I think that view, I'm caricaturing it, but I think that view stems from a sort of lack of knowledge, or in some cases disinterest in psychology and cognitive science, because there's lots to think about the mind, even not talking about neurons. That's not about subjective experience, and it's sort of like there's this whole missing chunk of knowledge that.
I'm just going to plus one on. I'm not sure how you do plus one on a podcast, but I'm going to plus one on what Sam was saying, and just add that if neuroscientists are going to give up on the brain side of subjective experience to think is what episodic memory people look at, there's a whole load of people in neuroscience that investigate that from a non-computational perspective. Then if we can't think of that computationally, then we failed, right? Subjective experience is part of the brain. And so so I think that on looking at it both ways wrong, Sam and I probably disagree with you about the statement that you just made there. Right? Is that fair, Sam? Or?
Yeah, I was making a different point, which is just setting aside the validity of subjective experience as a topic of study. I'm just saying that the view that mind is subjective experience, I feel like permeates the thinking of many neurobiologists, and prevents them from really engaging with the cognitive aspects of brain function.
But Paul, I want to bring back the big point to you. You said sort of like, you guys are into computation, isn't that super sterile? And isn't that far away from the subjective experience? The whole premise of that is that for some reason, just because we use mathematical tools, we are further away than, say, an experiment. And I just don't want to accept that as an assertion. So basically, just because our favorite tools is an equation, that doesn't in any way make it more sterile or further away from reality. Like if I did an experiment.
Equation is not the way we study the brain. The equation is often stating a hypothesis that we then go and test experimentally or in other ways. It's a tool to ask questions really precisely.
So let me just back up, Paul, for a second and challenge
Why is this all on me? I'm just asking questions. I don't have a position that I'm coming from that math is sterile and experiments aren't or something. But I'll take that. I'll be that person. I'll be the punching bag here.
You're a professional podcast host, so every word counts.
A provocateur. Yeah.
But let's say we're studying the kind of thing Yael studies or Sam studies, where we have what we really want to understand is the graph of the experience of the task or something like that. If we didn't need equations to be part of this, then we would design our experiments very differently. It is unfortunately true that we do have to design our experiments to be tractable to the equations that we want to investigate. And sometimes they do end up seeming a bit dry. And drier than they would do if we weren't making these precise computational statements.
What does dry mean? Oh, sorry. Go ahead.
No, after you.
Oh no, I was just wondering. Sterile and dry; these are terms.
Mechanical.
I'm not exactly sure.
Insults.
Not if you're
fine. I gathered that, right? But it strikes me that, I mean, it really depends on your cast of mind. I mean, some people find the mathematics enthralling. And
that's right.
Right. And so I'm not going to make a value judgment about it. You know, some people like it and some people don't. That's fine.
No, that wasn't the point. I mean, so I think the maths is fantastic, but I think that the fact that we're trying to get to that level of prescription means that we have to do experiments that are not naturalistic often. Yeah, exactly.
But we can take the two of them totally apart. And like we can do naturalistic experiments with stuff that is really like real life using math, because that's the precise way of asking questions. And we can use absolutely boring, trivialistic lab tasks without touching a line of code or math. So I just think this like perception, not like, sure, computation is hard, and that's why people go to Neuromatch and learn about it. But that like the magic isn't diminished the slightest bit by that. And I think that's important.
I think you're mischaracterizing what, at least to me, from my vantage point, the computational aspect is the magic. That is the top level, what everyone should be doing, how everyone should be thinking about brains. And I don't see any evidence to counter that.
I would say that it's not magical, Paul, because magic implies that there's something you don't understand.
We're going to quibble over words.
Sorry, I understand. Why don't you lead us back to the substantive
This is actually really important. I think this is really important. And I think this is one of the things that the goal of a course like Neuromatch is to make it not look magical, because magical seems like something that I can't do myself. And Konrad said the math is hard. Lots of things are hard. Doing experiments is hard. A lot of it is hard, but it's all learnable. And I mean, different people find it easier to learn different things. But I think, I mean, speaking about Bayesian inference, you asked in kind of the email that you sent us, one of the things was, what did we struggle most in our career? And one of the things I was kind of laughingly telling myself, it's with Bayesian inference, with Bayes rule. Like I knew Bayes rule, and I sat for 2 years in the lab where I was as a graduate student, and people would talk about Bayesian inference every day pretty much, or every other day. And I would be like, how do they always remember which part is the prior and which part is the posterior? And like, those didn't make sense to, like, I understood, I could derive the equation. It's a very simple equation, but I didn't have the intuition for it. And then at some point, it clicked. And now I I see it and I understand it. And so it used to look like magic to me, like magic in the bad way of I don't know what's the input and what's the output. How do they compute these probability distributions? What goes in? And for me, one of the things that makes it easy and lose the magic and become I can use this as a tool and I can understand this, it's to just write down the code. And literally it's I have everything I need. The prior is just the result of the previous iteration, and then I multiply it by something that I know, and then I divide, I once you put it all in code for me, then I'm okay, Now it's not magic, and it's good that it's not magic. I don't want it to be magic. I want it to be usable. And I think that's one of the things that hopefully students got out of the lectures and the exercises in Neuromatch.
I'm sure they've done this, but I used to, I should do this again, actually. I'm sure the Neuromatch kids have done this, but I whenever someone came to my lab, I used to tell them to spend the first week just estimating the mean and the mean of some data and the standard error on that mean, using all the different flavors of Bayes. And it takes from sampling techniques to direct integration techniques to analytic. You can do that particular exercise in about 10 different ways. Once you've done that, you understand a lot about Bayes. It takes, I mean, obviously doing that properly will take more than a week, but just once you know how to estimate, that's the total joy of Bayes, right? Once you know how to estimate the mean of some data with Bayes, you can do everything with Bayes because it's just about specifying a different generative model.
Tim, if you have that like exercise or assignment in writing, I totally want it.
I can definitely. I mean, it's really not hard to make. I can really make it. Yeah, exactly.
Yeah, I love that. Thank you. Yeah.
I was going to say, Yael, next week that's when your child is going to come to you and say, I know that my brain can update to do Bayesian inference, but why can't I understand it? And then you'll give the child those exercises. But
yeah, no, my kid is super magical. That is magical.
Well, okay, so let's get off of magical because that was just an error, I guess, on my part using the word magical because the real magic is not real. But let's go to coolness, okay? Because let's call it cool. I have a friend who runs a lab, and he and I were talking about how when we went into graduate school, we didn't have any coding experience. And now he says all of the kids coming in, they're all like machine learning experts. And that's because deep learning is cool. And so that's what I was talking about is the computational approach is the cool kid, is the cool way to do the popular kid in neuroscience these days.
And that's so different. I mean, when some of us here who are older than others here, were growing up as
right.
Early career scientists, I jokingly say, like, if you said I'm a computational neuroscientist, people would go talk to someone else in the party, right? It was like, this was not the cool kid. Nobody wanted to hire computational neuroscientists. Nobody was really sure what computational neuroscientists were. Very few universities had a computational neuroscience program. There were some summer courses because that was like, let's get people into the field. So computational neuroscience always had like its fair share of summer courses, but that because there was nothing else, you couldn't study it anywhere else in some sense. And it's amazing to me to see also like reinforcement learning. Nobody used to talk, even in a computational neuroscience summer course. I remember I was a student in 2001 in the European computational neuroscience summer course. It's now the Cajal course in Portugal. It was then in Italy that year. And in the whole course, we did not have anything about reinforcement learning. Nothing. Like a 4-week course. And in the last week, they asked us for feedback. And I said, you kind of missed the whole like area. And now it's such a hot topic. It used to be that you would find like at SFN, maybe like 10 posters of interest. And now there's a whole session every day that's like mostly reinforcement learning stuff. So there's been a huge change in the field, and it's really amazing to witness.
Kind of scary as well. It was kind of nice when it was just a few of us.
Can I actually say something about coolness? I mean, obviously I'm very gratified that people think, or at least some people think that computational neuroscience is cool. At the same time, I also think that when it comes to some specific choice of research idea, I think if you want to be really original, you're going to have to give up some coolness. Right? There's a tension fundamentally between being cool and being original, because there are many people who are entering the field kind of swept by this wave of enthusiasm for certain ideas like deep learning. And what that means is that many people are basically doing more or less the same thing. And I understand that particularly for young people who enter in and are trying to find some promising topic of research, it's natural to gravitate towards the cool things. But in some ways, I hope that we can train people to resist that to some extent and think about original ideas.
when I started my career, everybody was doing vision. Everybody in computational neuroscience was doing computational vision. And I was like,
that's still the case though.
But I remember saying to myself, I don't know what I want to do. I know what I don't want to do. And that is that. And it was almost just because everybody was doing it, and that just pushed me away. And look where I ended up and what everybody's doing now. But the other things I wanted to say, Paul, to what you said, that like now it's cool and everybody comes in knowing how to program and having programming background. I just wanted to say for those listening that not everybody, actually, right. A lot of women, it turns out, don't have programming background. Also some men, but that's totally fine. It's so learnable, and it's not like you don't have a place in this field if you don't come with this background from home. There's this perception that everybody has it, but it's really not true. A lot of people in my lab don't have programming background, came without programming background. You know, Sam came from psychology and kind of a lot of self-learning as a programmer. I have other students coming from math. I almost have nobody. I actually, in my lab, I think have 0 people who came from computer science. So programming background is not the requirement to do this kind of work.
Well, that's because psychology is such a soft, magical. What are the other? But Konrad, I didn't go ahead. What were you going to say?
Yeah, I wanted to zoom out a little bit. So there's a computer scientist, Dijkstra, who's one of the big heroes in my life, and he formulated 3 rules of what you should do to do good science. And it's highly debated, and there's a lot of people who disagree with. But the last 2 things we just said perfectly mapped on 2 of his. The last one we discussed is like, yes, coding we need to often learn to be able to do the research that we want to do. And one of his rules is you should always do the hardest and most complicated research that you can possibly do, because that's the only way to grow as a scientist. And the other one is, when given a little bit of time, someone else will solve a problem. You should move away and do something else, which is what Yael told us to do. In a way, being in an area where lots of people are doing the same research, you shouldn't be there. It's a waste of mankind's resources. And it also pushes you into that space where you have to compete on the number of hours you spend per week instead of the clarity of the ideas that you can bring to it. Because these overcrowded fields, there's always other people doing roughly the right thing. And it's just bad because people compete on the wrong things.
But Paul was saying that that people go to what's cool. And I want to push back a little bit, Konrad, on this strategic idea of you choose an area to maximize what humankind will discover. I think we choose areas based on what we are super excited about. And it's true that if there's an area that a lot of people are working in and giving great, exciting talks on, then students get excited about it. And I wouldn't say don't do something you're excited about because the competition will be tough.
It's not just about the competition, but it is, you see, neuroscience is so big. When I started in the field, I had no idea how big that is. So it's really weird that there's these bubbles where all of a sudden you have dozens of labs doing very similar research. And I understand it feels comfortable with a lot of people sharing a certain set of ideas. But I've been part of these bubbles, and it feels at the end of the bubbles, well, maybe we went a little overboard into that direction. So I do think that having diversity of ideas is really incredibly valuable. And that's why if you find an area where lots of people congregate, and that's just my own opinion and Dijkstra's, that in a way we want to see if we can bring in new ideas and do something that is somewhat different. And Yael, you told us that you were okay, I don't want to do vision because everyone else is. And you were incredibly off the charts successful at charting new ways of doing things. And I think that possibility exists in a lot of areas of neuroscience.
But it's not that I didn't want to do vision, even though I was excited about it. I just wasn't excited about it. Something about it did not excite me, maybe because it seemed to I don't know why. It was just the one thing I wasn't excited about. I was excited about pretty much everything else. And I was most excited about reinforcement learning. And I ended up doing that. I'm just saying that, I mean, I think people often try to think, well, I don't know if often, but people sometimes ask me whether I chose an area of research strategically or something like that. And I feel that it's really hard to predict the future. And if you're in an area that's crowded, and that's what you're most excited about, then you can remind yourself that we are not at all close to understanding the brain. So there's room even in that area. And if you're excited about something else that not everybody's excited about, good for you as well. You will, as Konrad, as you were saying, you will help push mankind forward by doing something that not everybody is doing. But really, it's very subjective what we get very excited about. And I would encourage people to not try to overcome their excitement with strategicness.
Well, it's funny because I was thinking in some ways of the inverse of what you're saying, in the sense that, yes, there's a subjective element. First of all, I agree with you. People should do what they're excited about. In addition to the subjective element, I think there's a lot of path dependence about what people are excited about. And I'm excited about things today that, if you had asked me 10 years ago if I was excited about those things, I would say definitely not. Why would anyone study those things?
Is that single cell learning?
Yeah, and I mean other things like I did work on motion perception. I didn't think that motion perception was particularly interesting, but it turned out that there are things that were interesting about it for me. But that had a lot. Again, it was very path dependent because I came to it from a particular angle that was driven by other things that I did that were not about, let's say, motion perception. And then the other thing is the other way in which I was thinking about this in a kind of inverted direction from Yael is that I think there's often a strategic aspect to why these sort of bandwagon effects where people pile into one particular research area. And because I think people see what produces successful careers, and they have some anxiety, like, should I be doing this obscure thing that nobody cares about, or this thing that not just I'm excited about, but many other people are excited about, it will advance my career? And so it takes some degree of courage to and acceptance of risk to take the leap into an area that maybe you're excited about, but you're worried that it's not a good career move.
On the path-dependent thing, I just wanted to say that my interest in reinforcement learning came from a paper that I presented in a seminar. And that seminar started my whole career, an undergraduate seminar. And I don't know if this is true, Sam, or not, but I feel like when you joined my lab, we had these like mini rotations of like 2 weeks in each lab, in a few labs in what was then we didn't have the Neuroscience Institute, the psychology department. And I gave you a paper to read about young rats doing extinction differently from old rats. And I kind of feel like that started your model and your whole PhD thesis from there. So I don't know, maybe you had those ideas already to start with, but I felt like after that, I kind of thought, wow, I should think really carefully what papers I give people because, one paper goes a long way here.
Oh, yeah. I mean, I realized that too. Like I would sometimes throw off a random idea and some students would work really hard to sort of figure out what my cryptic half-baked idea was about. When my intention was not to set people off on this odyssey, but so it gave me pause to think about the effects of casual suggestions.
Well, I'm very happy I gave you that paper. The path dependence there worked really well.
Me too.
Can we talk about questions for a second? Because you hear over and over when someone asks what model should I use, the answer is always it depends on what your question is. But a lot of people early on in their careers think, oh God, I need a question. They don't have a question, right? But they have a vague interest because deep learning's cool or whatever, in the brain and computational neuroscience. And then, so I don't know if you can say this from your own experience, thinking about path dependency and the nature of how your questions have changed over the course. Did you come in with the right question? Did the right question develop through one of your advisors giving you a paper about rats, or how did that work?
I think everybody has to find, particularly with a new PI. Yeah, I mean, I wrote a little thing about this actually. But I think it's the bigger, if you're still working on the same thing you told your hiring committee you would work on 10 years later, then something has gone wrong, and probably. Most people find their questions because their data don't make sense without different questions. I think. There are some people like Sam who are so broadly read that they can find new questions from out of left field. But I don't think that I'm certainly not like that. I look at data and it doesn't make sense. And I was led to, for example, from frontal cortex into hippocampus because it was the only way I could make sense of frontal cortex data.
But do you remember like the initial part of your career when that sort of stuff, before your questions were well formed? Do you remember feeling, oh, now I have a question and
it took me ages. It took me ages to start working on something that was actually. So I was working on various sort of things that were just like little individual projects that were just related to what I was doing in my postdoc, and just worse than in many cases, but often related. For the first 5 or 6 years of running a lab, they were fine. They were just isolated. There was no deep understanding to them. In some ways, maybe I did them for safety because I knew they would work, and they were related to what I'd done before. But during that time, I formed a lot of deeper, I think, questions about how going about how to go about these things, and I think that really that comes from like serially seeing data and it only making sense together with some deeper question. I think that if you don't, questions don't magic themselves up unless you read an awful lot. That's the other way that maybe you can get questions.
Yeah, I was going to say that reading is another source. Sometimes it's your own data. Sometimes it's kind of an observation of a phenomenon in the world, or, since we're studying brains in our own like subjective experience that brings a question. But a lot of it, I remember at some point saying to a colleague that I don't have any new ideas. And then like in a different conversation, I said that since my kids were born, I haven't had time to read papers. And she was like, well, no wonder you have no new ideas. Where do our ideas and questions come from? It's from reading other papers or going to talks.
I have a friend who would directly contradict you, who swears that reading is the devil, and you generate your own ideas, and then those generate new ideas. He does not read. He runs a lab. So just wanted to, as a counterpoint.
But does he go to talk?
Quite an arrogant perspective. It can work for some. It worked for Jeff Hinton, but it doesn't work for everyone.
Depends what you mean by work. I mean, if working it also involves forgetting everything that other people do.
I think there's this diversity of where questions come from. Like questions come from, often questions for me come between fields. There's this field that says this field that says that. How does it even fit together? Sometimes they come from reading. Sometimes they come just opposite direction. You look at data, you're like, what's the question that would go with the data that I happen to have? And that's also a perfectly fine way of getting, not in the overfitting sense, but like we can measure A and we can measure B. What's the set of questions that you can answer if you can only measure A and B? And it's a different set than what you start with. And I don't think this like notion of like the question is fast and us trying to answer it is later maps on all projects in neuroscience.
I think it's really important to have a question. I mean, yes, it can come from different places, but I don't know. I mean, this might be subjective in how different people do science, but I feel like if you're doing a project and you don't know what you're asking, then you're unlikely to find an interesting answer.
I totally agree with that. And actually, something that I've started doing, I realized reviewing lots of PhD applications, this might actually be something useful for the Neuromatch listeners out there. I realized that the vast majority of applications, when they write their research interests, they say, I'm interested in memory or decision-making or whatever. And the problem there, I think, is that when you sit down on day one of grad school, you can't just sit down at your computer and start working on memory, right? It's not a question that can be answered, right? And so I started, for all the undergrads that work in my lab over the summer and are thinking about applying for grad school, when I talk to them, I ask them, what is their question? And usually they don't really have one. And so I tell them to think about it and then talk to me again later. And then we basically talk about it until they have a question. You know, it's not necessarily the question that they're going to work on for the rest of their lives, but a question that we both agree is good and interesting for them. And I think that's actually a really useful approach to writing, to preparing PhD applications, and also to know who you want to work with, who's answering the question that you want to answer, or who are trying to.
It's amazing, though, that you're doing that with undergrads, because I want to say that I ask postdoc applicants, what question do you want to study? And many postdoc applicants don't have an answer to that. It's really hard.
Yeah.
People will know, what method they want to use or what kind of thing they're interested in, but often they don't have a question. Again, I think it's really important to find a question to do research, but I again want to, say to the listeners that if you don't have a question, that doesn't mean you're the outlier. Actually, most people don't have a question.
We should tell everyone about how Dickinson found his question for the devaluation experiment. I guess.
How did he? I don't know the story.
The watermelon story. You've not heard the watermelon story? No, I'm joking. Yeah. We shouldn't tell that story. We only have like a few minutes left. But it was like an anecdotal personal experience that had to do with drinking with drinking too much and having a hangover.
But I want to emphasize here that there's a process that we can have that helps, that makes, at least in my experience, the finding of questions easier. So I force everyone, before they do real research, to write an abstract which contains a question and the answer that they're expecting for it. And this forcing yourself into just put the story that this will be into 100 words, that really forces people into coming up with a question. And I found
are you guys not forced into that? So we have
a very cool idea.
But we have to do this institutionally. Whenever we start a new project, we have to, the graduate student has to give a presentation to the whole department before he gets any data or does anything on it.
What does a new project even mean? That's what I was going to ask Konrad, but I guess you as well, Tim, because Konrad, you said before anybody does real research. What's real research versus fake research?
I want people to write an abstract before they do one line of coding.
Oh.
Any coding. Interesting.
Yeah. I ask people to do more than that. I mean, I ask people to write down their whole model before they do a piece of code.
Coding is the new real research?
I don't ask anybody to do any of that stuff. I must be doing something wrong.
No. I mean, they're different styles. It's not one size fits all. It's for certain kinds of projects that, this is neither here nor there, I suppose. Yeah.
Well, we have to present before we get data. So for the data part of it,
for any experiment or just for fMRI experiments, if you're going to collect some data on Mechanical Turk, you have to present to other people about it.
So you're totally right, Yael. It's for experiments on the it's mostly for experiments on the MRI machines, but we actually also do it for some of our rodent experiments as well. We don't do it for
that's different. That's different. Yeah. Like most of what we do, we get to an fMRI experiment once in a PhD late on in the game. Most of the work, and some people don't even, don't do fMRI their whole thesis. Like Sam, for instance, his thesis and my, right? You didn't do fMRI, or did you?
I did.
You did with Ken, but not with me. With Ken, but not with me, right?
I did, but those experiments didn't work out very well.
Yeah.
You wiped it from your memory.
You did fMRI experiments with me?
Guys, I have
I'll
to
tell you about it later now.
It's time to depart, but let's do a very quick experiment, a wet and dirty experiment. Let's test your predictive brains. I want to thank you all for being here. This has been blank. What am I going to say?
Inspiring.
Sterile.
Yeah, exactly.
Magical.
Magical. Sam got it. It was magical. So I don't know. That was kind of a low accuracy experiment. But any parting words before we hardly talked about anything except fun stuff. So any parting words specific to anything, any of the topics anyone was learning this week or otherwise?
I'm going back to the beach.
And have fun would be my parting word, both for Tim and for everyone listening in here.
Find your question. It was the one of the themes there. Well, thanks very much, guys.
Thank you,
Catch you
Paul.
later, guys.
Thanks.
Bye.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The stair